Right. Now, what's interesting about mass spectra is the fragmentation patterns that we see, because these are often indicative of the structure of a molecule of which we're observing the mass spectrum. So, I've said in the previous lecture that we can predict that the electron that will be lost upon ionization is likely to be a lone pair. If there are no lone pairs, then it will be a pi electron. If there are no lone pairs or pi electrons, then you will have a sigma electron that is lost. And what is further interesting in this is that we are able to show mechanisms of fragmentation. So I'd like to go back to the mass spectrum of methanol and remind you to always on mass spectra to look for the base peak, which is the highest peak in the mass spectrum. That's normally scaled to 100%, and the molecular ion, which we can check by simply adding up the masses of all the atoms in the molecule to confirm. And for methanol, the molecular ion is at 32. But I want to go further here. I want to try and predict how we see this molecular ion at mass 32, how we could see this fragment at 31, and how we could maybe even see this fragment at 15, how those get formed. Of course, one could also try and explain why other fragments are formed, but that is beyond the scope of this course. So, what we need for this is a mechanism. And here's, I'd like to run through how this mechanism occurs. Don't forget that when you put a methanol molecule in a mass spectrometer, it gets bombarded with a high energy electron. And of course, we then need to decide what electron we're going to lose. Well, of course, the easiest electron to lose is a lone pair electron, and of course in methanol we've got two lone pairs. Okay, so what happens is I'm going to then knock off this electron on the left here, you can see here, and so what you see over here is a positive charge where that electron has been knocked off. Okay, right, so what happens next? Well, let's stop at this point, because this is a charged system at the moment. So we've got our molecular ion over here. Its mass is 1 plus 16 plus 3 plus 12, which is 32. And if we do a mass to charge ratio, which is what mass spectrometers work, it is 32 divided by 1. It's charged, so it'll be observed, and so we have shown that how we get M over Z in the mass spectrum of 32. So the 32 has fully explained at this point. Simply by removing electron, we've got a positively charged molecule, and so it will appear in the mass spectrum. What happens next? Now, I want to remind you that when you look at mechanism, we can use either full arrows or we can use half arrows. Full arrows indicate the movement of a pair of electrons. Half arrows indicate the movement of single electrons. So be very careful when you use full arrows or half arrows. Now the first thing that can happen is homolysis, or a movement of single electrons from a bond in a symmetrical manner. So see the two electrons in this bond. What we can do is we could take the one electron using a half arrow, a fishhook arrow, and that electron will end up on the hydrogen to form a hydrogen atom, and the other electron will join this electron that is over here and will create an electron pair. So if we do that, you can see we form the pair of electrons here from the one, and of course the hydrogen atom is a radical in its own right, one electron around the nucleus, and of course it has no charge. When you move electrons in this way, charge does not change, and so you'll see that the charge remains where it is. Homolysis does not allow for movement of charge, and so what you end up with is this even electron cation. This is a normal cation, but of course what's happened is its mass now is 31 and its charge is 1, so we can calculate a mass to charge ratio of 31, and of course this has no charge, so it's not seen. So we now know the fragment that is giving rise to the peak at 31, and we know from the mass spectrum that this is the most stable fragment during the fragmentation of methanol. Right, now the way that this can fragment now, because we don't have radicals, we've no need at this point for using half arrows. One way that this can fragment is using where this full electron pair goes and neutralizes, it goes to the positive charge. So there will be movement of charge from so the movement of charge will be, so that the fragments, one fragment will end up with different charges. So both of those electrons move to that side, leaving the left hand side positive, and so you'll end up with M over Z. So the mass of the methyl cation is 15, its charge is 1, 15 over 1 is 15, and so we'll see a mass to charge ratio in the mass spectrum of 15. But of course we've neutralized the charge here. The oxygen atom that is formed, the oxygen atom has no charge and will not appear in the mass spectrum. So now that explains how we see M over Z of 15 in the mass spectrum. Okay, so what we have managed to do is we have managed to rationalize or explain why we get peaks in the mass spectrum at M over Z 32, M over Z 31, and M over Z 15. And of course, in doing so, we've had to use the fishhook arrows showing the movement of single electrons, and we've had to use the full arrow showing movement of pairs of electrons.